Thank you for coming, despite New York's deadline coming up very, very soon. So it's our great pleasure and honor to welcome Professor Stuart from CALTECH today. Andrew, the floor is yours.
Thank you, David. Thank you for inviting me. I know the title of the program that you're all involved in, although I can't quote it exactly. I think I touch on some of the subjects. There is some machine learning in here, there's some uncertainty quantification, and it's a nice small room, so just interrupt and ask questions. I'm going to talk about score-based diffusions, and I think the main take-home message is that this is an area where, if it is to be used beyond the specific situation where it's been heavily developed, which is generating images, then more theory is needed to regularize the algorithms that are being proposed. So I'm going to explain to you some failure modes of score-based diffusion models, explain how regularization is employed in practice, and describe some directions that I think come out of this where theory could generate more principled regularization. That's the basic goal. And the failure mode is memorization. So I'm going to explain to you how and why memorization happens in diffusion models. And as a part of that, you'll see the need for regularization. So at the heart of this, it's an inverse problem, but it's a complicated inverse problem because it's involving the diffusion methodology for generative modeling. So I'll spend some time explaining that. And apologies to those of you who have expertise in that area. So the work I'm going to describe is based on this paper, which is joint work with Ricardo, who is soon to be an assistant professor at University of Toronto in statistics, and is currently a postdoc working with me at Amazon, in fact, and prior to that was in CALTECH. Agni is a graduate student at USC, and he's about to become the John von Neumann Fellow at Sandia, which is a postdoctoral position. Nick is a former student of mine who's about to become an assistant professor at the Courant Institute. Assad is Agni's advisor at USC, and that's me. Okay, so the topic is generative modeling. So let me just explain, even though you all know what that is, set up some notation. So I'm going to assume we have a probability distribution on RD, call it P0. I will be a bit vague about whether I'm talking about the density or a measure. Just let me have that vagueness if that's okay with you. So probability measure on RD, and we're given n, uppercase N samples from that probability measure. That's the data. Here is an example. And the goal of generative modeling is to create new samples from P0 that are not present in the data set. Okay? That's the statistical problem. Any questions about notation? Okay, so I'm going to talk about diffusion models for doing this. And this slide here is just to show you two applications. One that okay, I'm not going to say that because I'm being recorded. Two applications. One of them is teddy bears and the other one is science. But in either way, these are pretty impressive things that are being done with diffusion and conditional diffusion-based generative modeling. I personally would not want these pictures on my wall, but as a piece of science, the fact that we're able to generate images like this, often conditioned on text, is pretty amazing. And there are interesting scientific applications. For example, this is an example of what's called, it's called downscaling, which is confusing, but also known as super resolution. So taking images and adding fine scale features to resolve them at a higher pixelation. This is a canonical paper in this area. It's a stable diffusion paper. That is an example paper, not canonical. And by the way, I'm happy to make the slides available if you want to follow up on references. But there's lots of evidence that diffusion models memorize and lack diversity, especially when they are conditional. I'm not going to talk about conditional, but the theory that I present can be generalized to the conditional setting. And the things that happen in the conditional setting, you can see from our theory that will be in a follow-up paper, are even more severe than you're going to see in the unconditional setting.
Sorry, when you say conditional, you mean like these guided diffusions?
Yeah, so often conditional on, for example, text is the canonical thing. So that's done by learning a score conditional on a piece of text or something of that type, which is done with a, there's a number of ways of doing it. They can be guided, as you say, being one of them.
But this is not necessarily only that, it can be other ways.
Yes, it can be, yeah. But I'm going to talk purely about unconditioned in the talk. But lots of these examples actually come from conditioning. So this is an example from this paper of a generated image and a point in the data set, and they're clearly pretty close. For companies, this is worrying because they don't want to they're going to fall foul of copyright if this happens. This is a more subtle failure mode where here you see generated images that are clearly related to the training set, but they're perhaps on a slightly different scale. So things have been added to this image to create this image, and this image to create this image. But nonetheless, there's a clear element of memorization in what you're seeing here. Okay, so I'm going to describe the diffusion model methodology. I will then focus on the question of learning the score, which is what makes this into a practical method. To analyze the phenomenon of memorization, I'm going to talk about time change, and then I'll explain the main theorem. And this is really, as I've said at the beginning, this is an indication of the need for regularization, and we'll then discuss that. I will write a couple of things on the board so that we can remember notation. So I'm going to start with this slide on the forward process. And I'll explain, this is just, I'm just going to build this up through a theory of SDEs and then explain how it's used to do generative modeling. But here, I'm just going to assume we have a stochastic differential equation of this form. F may depend on the state X and on T, and the noise does not depend on the state, just depends on time T. I'm working within this class because the two most commonly used examples are subsets of this, and I'll come to one of them in detail later. And assume that x of 0 is given by sampling from P0. P0 is the thing. Eventually, we're going to try and approximate P0 through samples. But for now, just assume we have P0. And now we can ask, how does the probability density function of x evolve? Well, it evolves according to the Fokker-Planck equation. So P here is an element of probability measures on Rd for each fixed time t. And given this SDE, it will evolve according to this Fokker-Planck equation, started at P0. Any questions about notation or anything? It will, yes. So the two main methods that are used in this context are when f is 0 and this equation is integrated until the noise is large relative to the size of the data, or time-dependent OU process where this vector field is linear in x and proportional to g with constant of proportionality g of t, and then you integrate till you have some exponential decay that kills the initial condition relative to the noise. So both of those cases are the most commonly used, and they're included here. Okay. So now I want to think about reversing that process, because the methodology we're going to use is to take samples from P0, run that equation forward, and then reverse it. And I'm just going to postulate that we should add something related to grad log P to reverse the process exactly. And I'll show you that that's possible with a very simple calculation. But for those of you that do sampling. This is natural. And okay, this resonates with Langevin equation. So let me just say that. So I've taken the original equation and I've just added this vector field where P is the solution of the Fokker-Planck equation on the previous slide. And I've added a scaling of the noise here, and there's a free scaling parameter alpha in this term here. And I'm going to run this backwards. So I view this SDE as starting at time uppercase T, where I'm going to start it for now at the distribution given by the solution of the Fokker-Planck equation forward on the previous slide. So I call that P sub T is the solution of the forward Fokker-Planck equation at time T. Now I'm viewing this as a reverse process going from T to 0. So I'm now going to write the Fokker-Planck equation for this. With respect to the drift, it's exactly the same as the Fokker-Planck equation on the previous slide. Yes, go.
So when T, the Fourier can be like here, do I do T or minus T?
No minus T. I'm just integrating it from uppercase T back to 0. Okay. So I'm running it backwards in time. Yes, that's the right. Turns out to be the right sign. Otherwise, the alpha values will be positive with this choice. So if I run this backwards, the contribution from this part of the drift is the same. This is a new contribution from this term here. By new, I mean in comparison with the forward Fokker-Planck equation. And because I'm running the SDE from T to 0, the sign of the Laplacian is negative. Okay, so this equation, under some regularity conditions on F and P, is well posed, viewed as an equation backwards in time, starting from T, uppercase T, and integrating back to 0. Okay? And now you can, yes. In the original Fokker-Planck, it's positive. Yeah, because I'm integrating forward. Here it's negative because I'm integrating backwards. So if you were to integrate, just think about Brownian motion. If you integrate Brownian motion backwards from T, uppercase T to 0, the density will evolve according to the heat equation with this sign and be well posed in that direction. Okay, now what I would like, and this is the key to diffusion-based modeling, I would like the solution, so that the solution of the forward Fokker-Planck equation is P. It enters this diffusion process and therefore enters its Fokker-Planck equation, which has solution rho. What I would like is for the solution of this equation integrated backwards to coincide with the solution of the previous Fokker-Planck equation. So I would like for rho equals P to solve this problem. That means that I would like that if I put rho equals P into here, this equation becomes that equation. And that, if I have uniqueness of the Fokker-Planck equation, will prove that when I solve this problem backwards from T as 0, starting from PT, the solution in law at every time will be the same as the forward process.
It's the same as the backward formula.
It is, so it is the backward Fokker-Planck equation rather than, so in theory of SDEs, often the Fokker-Planck equation is written forward and Kolmogorov is written backward, but that's not, that fact is not really relevant to this. So here I am, the reason I'm going forward and backwards here is because literally I'm integrating forward in time on the previous slide. And now I'm integrating backwards in time. So this is a well-posed PDE under regularity assumptions on F and P. It's a well-posed PDE for rho. But I'm going to ask that what is the conditions on alpha and alpha 1 and alpha 2 so that it is solved with the same P as the forward process.
Can we be sure that alpha will scale before it will be?
No, so this I'm not saying this is the only way to do that, but I'm saying that if you postulate this process, I'm now going to find what conditions we need on alpha 1 and alpha 2. So there's a paper by Anderson in 1982, which I will explain or reference in a moment, which is possibly the canonical reference on this reverse SDE idea, although there was work prior to that. And the paper of Yang Song and Stefano Ehrman and others that developed the diffusion-based methodology basically copies the Anderson approach. What I do here is a quick way to get to the right answer, which I find understandable. I'm trying to convey it and make it understandable to you guys. So the key thing that's going to happen here is exactly the thing that is in Otto's analysis of Fokker-Planck equation, and that is this. So I want this to have solution rho equals p. If I put rho equals p in here, you see that grad log p multiplied by p becomes the gradient of p, and this will give, if p rho equals p, this will be grad p, and then this term will contribute another Laplacian of p. And all I want then, I'll have alpha 1 times the Laplacian of p minus a half alpha 2, sorry, times g the Laplacian of p minus a half alpha 2 g Laplacian of p. So the conclusion from this is that if alpha 1 minus a half alpha 2 equals a half, then this equation will have solution rho equals p. Go ahead.
So the alpha 2, they would completely cancel each other, but we should still have the origin from that will have the Laplacian.
Yeah, so the other, here there's no alpha, there's a half. So I want to get a half out of this. So if rho equals p, this is just grad p. So I get an alpha 1 g Laplacian minus a half alpha 2 g Laplacian. So therefore, alpha 1 minus a half alpha 2 has to be a half. And that's the essence of it. I would say this calculation is the best way to see what's in the paper of Anderson and Song and Ehrman. And there are infinite dimensional versions of this, so it's much more complicated than this simple setting. So this is this proposition. As I said, this is the paper of Anderson that I'm referring to, but the proof is not the way I've given it. And I have not given the proof properly because you need enough regularity for those two equations to have unique solutions. But given all that, what we've shown is that if alpha 1 minus a half alpha 2 is a half, and p is the solution of the forward Fokker-Planck, rho the reverse process, then the marginal distributions of the forward and reverse processes agree. That's what's really needed, and that is rho equals p. And then that suggests an idea, which is in this paper of Yang Song and others, which is to sample from p. We're going to just approximate the whole picture that I've just shown you. So we're going to choose firstly choose a forward process so that at time t, the law is approximately a Gaussian with mean 0 and some variance that will depend on t. Also choose the forward process so that sampling from it marginally is straightforward. The whole methodology does not require sampling of paths. That's what makes it efficient. It only requires marginal sampling at any random time in 0t. Using this, we're going to learn from data. So this is the inverse problem embedded in here. Learn S dagger, which is grad log p. That was the thing that appeared in the reverse process. And then since this is all set up so that the law of x of t is approximately Gaussian, then we can just run the reverse process back from this Gaussian, sampling from this Gaussian. This, I should have written this in the bullet. This whole thing has to work. So what do I mean by choosing a process so sampling from it is straightforward? That means two things. This is a condition on the forward process. Firstly, we have to be able to use the fact we only have P0 empirically. That's fairly straightforward. Every empirical sample will give rise to a trajectory of this equation given a choice of Brownian motion. But also, essentially, in the methodology, we want the solution to be Gaussian with explicitly calculable mean and variance so that one can sample marginally from the process conditional on P0 starting at a data point. Yeah, so the two choices are an OU that are made are an OU process with a time-dependent decay and variance, or just no drift, and that they call that variance exploding, which is, I will concentrate on variance exploding, where the variance just grows to a point where it's much larger than the size of the data. Those are the two things that are done. So you either kill the initial data by adding noise that's much bigger than it, or you do an OU process. So that's exactly what they do, those two. Any questions about this? Okay.
This whole reversibility story that you just told us in a much easier way by knowing this is an OU process.
Yeah, so I've written it generally because, so this is much easier than the Anderson paper for the general case. And this, so I like this explanation for that reason. But certainly if I just started with OU or variance exploding, I could do it even more simply. Okay, so what is done then is that I'm going to write down some loss functions, but they can all be, the goal is to get them to an empirical place. Okay? So, but here is a loss function that patently has as minimizer the thing we want. So just integrate the average. This is with respect to the distribution of x started from P0, the difference between S and grad log P. So the minimizer of this is S is equal to grad log P. So I want to try and minimize this. Now it turns out that this is, I want to be able to do this empirically, and the next step is important for that. So let me write J0, where I just factor this conditional expectation, factor this expectation by conditioning on the initial condition and then averaging over it. That this I will replace empirically, and this is going to be Gaussian. So this becomes very tractable with samples. Replace, so this should also be gradient with respect to x. Replace this by the gradient of the log of the conditional density. So it turns out with a relatively simple calculation that J0 and J differ only by a constant. Constant is here explicitly. And so provided this constant is finite, the minimizer of this will also be the minimizer of this, and the minimizer of this is S's grad log P. Right? So the methodology that's used in practice is to minimize this using empirical approximation of x0. S. So this is a function of S. So at the moment this is non-parametric. I'm just writing it in a way where it's patently the case that the minimizer is the score. Because I can make this 0 when S is equal to grad log P. We'll come to what class of functions this is minimized over in practice. Yeah.
The x0 is going to be the data?
It's going to be the data, yes. Yeah, so this x given x0 will be a Gaussian. So as you say, x0 will be the data samples.
Yes.
X given x0 will come from the Ford process, which is this. So if given x0 means we're going to choose an x0 from the data and integrate this. And as just discussing with Richard, this will be integrated either with an OU process or of what's called a variance exploding process when f is large. I will concentrate on the latter. That makes sense?
Yes.
Thank you. Okay, so this is actually what we've just been discussing. No, sorry, this is not what we've been discussing. Although I said there's this parametric family, any choice of alpha 1 and alpha 2 that satisfy this will suffice for the reversal idea. But there are two canonical choices. One is alpha 1 and alpha 2 both being 1, where the reverse process is an SDE. And the other one being alpha 1 is a half, alpha 2 is 0, where the reverse process is an ODE. Okay, so this is an ODE, which if you initialize it at time t with the solution of the forward Fokker-Planck equation and you run it backwards, it will be equal in law to the solution of the Fokker-Planck equation forward in time. Yeah.
So how difficult it would get to do the reverse process if G was a function of X? Because I was trying something where the diffusion was function of X and then your R was on these figures because that would go inside with the constant in the term.
Mm-hmm.
G would go inside, right?
Yes. So what you're saying here, this G will come inside both of these. Well, it'll come inside here, but also in this term here, it'll be inside the. It'll be the, divergence of G rho. How easy is it to match them, or how easy is it to find a good choice of G?
Yeah, good choice.
I don't know the answer to that. I mean, I'd be interested to talk with you afterwards if you've been trying it. I've not seen any use of it, but there's so many papers in this field. The fact I've not seen it doesn't mean anything. So please tell me about it. Okay, so how this is minimized, we've shown that J0 can be minimized if you had all the data, and its minimizer would be the true score. So in practice, this is done empirically. So I'm replacing, as we just discussed, the expectation of X0 by empirical. So that's this is the empirical measure. And then this expectation is now, will be in a few moments when we get specific about F and G, Gaussian. Yes.
Will it always be Gaussian? So only the terminal one, but the trajectory, because we start with K0 and you go towards the Gaussian at the end.
No, it's going to be Gaussian. So it's not until I say that F is linear. But once F is linear, sorry, that's the reverse process, forward process. Once F is linear, this has a Gaussian, and I choose a fixed initial condition. For fixed initial condition, the distribution of this is Gaussian at each time, which is crucial to the method because you need to be able to sample from it. So in terms of the logic, I have perhaps jumped the gun by writing this, but in practice, F is chosen to be linear, so X given X0 is always Gaussian. In fact, I realized that I have jumped the gun because I'm now talking, this slide is slightly out of place. Oh, I see. Sorry, I've skipped. I'll come back to this figure in a moment. Oh, I think I might have deleted. I worry that I've deleted a slide. Oh, here it is. Okay, good. Sorry. I was talking with my colleague Ricardo about how when you're a speaker, you should know exactly what slide is coming next. I missed this one, I apologize. So I will work with the variance exploding process. All of our theory can be generalized to the OU case where F is G of T X, but it's more complicated. I'm just going to do this case. So the distribution then is Gaussian, and let's write this because sigma squared is going to come up a lot in where we go in the future. So sigma squared of T is the variance at time T of the process. So it's the integral from 0 to T of G of S. So everything I'm going to do now is for this, but everything can be generalized to the OU case. Okay, and then also I am going to talk about the reverse ODE, but I believe, although I have not completed proof of, but I believe that memorization will also happen in exactly the same way for the reverse SDE. But I'm going to talk about the reverse ODE. So the methodology that is used here is to run this equation backwards, starting from this Gaussian, with some approximation of grad log P, which is what we've been talking about here, how to find that approximation. Okay, so here I'm using the explicit variance exploding process form of this distribution. So the minimizer of this is no longer grad log P, it is Sn. So let me also write just a couple of things. So S dagger is the true score and Sn is the empirical minimizer. And it's a fact that follows in a fairly straightforward way from going back a couple of slides, that there's also a formula for Sn, which is a Gaussian mixture. So the way to see that is that if x0 is an empirical measure and x given x0 is Gaussian, then P of xt is a Gaussian mixture. And again, you can just read off the minimizer. It is grad log P. But if I'm empirical with respect to x0 and x given x0 is Gaussian, P is a Gaussian mixture. So the weird thing about this field is that you can write down the minimizer of the loss function that the field works with. So that the field numerically minimizes J0 when the minimizer is in fact known. And it's a Gaussian mixture. So when you realize that, you think, well, that's a bit weird. So in this field, we have this thing that we try and minimize, but you actually know what the minimizer is. So you can ask yourself, why don't you use the minimizer?
So when you say it's a Gaussian mixture, you mean it's the score associated?
It's the score associated with the Gaussian mixture.
You always write it as it's very general.
Well, if you allow integration, so it's a finite combination of Gaussians. More generally, of course, there's a wide class of densities that can be written by convolution, but this is finite.
You just use the fact that you know that the P's are quotients, and so in your minimization problem, you restrict this set.
Yes. So, well, as it is, if I minimize over some class, and I don't even have to restrict to that set. I'm saying something more than that. I'm saying that minimizing J0 is the same as minimizing J, provided K is finite. And minimizing J, if X is X0 is empirical and X given X0 is Gaussian, the minimizer of this will be given by just the score will be, well, P will be a Gaussian mixture and the score will be that of a Gaussian mixture. So if I minimize over some smoothness class that includes the Gaussian mixtures, then that is what I will find. So that's weird in the sense that you ask yourself, well, if you can write down the minimizer, why do you bother to minimize it with a neural network, which we'll come to in a minute. Any questions?
This is large dimension of the neural network.
Yeah, it's not practical to do it. So that's what will come up. Although there could be another answer as well, which is that the field didn't realize that there were, which I think is also probably true. The practical field didn't realize there was a pencil and paper minimizer to their objective function. But both things that we've said are true, I would guess. All right, so let me show you what are the problems with this, what I've just described to you. I'm going to take an example where P0 is N01, and in a straight line here is the score. So the score, because this is Gaussian, I take the log and the gradient, I'm just going to get a linear function, and that's it. So that's the exact score, and these red points here are sample data points. In blue is the Gaussian mixture score for a relatively small value of time, it's 0.15. And what you see is that it is a smooth Gaussian mixture in this case, which oscillates. It's a terrible fit to the true score. It's passing through the data which is given for training, but it's nowhere near this straight line. And furthermore, as t goes down to 0, this Gaussian mixture becomes more and more sawtooth and closer to a piecewise linear function. But at the same time as becoming closer and closer to a piecewise linear function, it's also blowing up. So I've scaled the piecewise linear function so it's on the same scale as the Gaussian mixture. But if you go down to t is 0, what you'll see is that what you learn, if you were to use the Gaussian mixture, is something which is a piecewise linear function which is growing in magnitude to infinity. Okay? So this is a terrible approximation of the true score. Right? So we're in this setting where the thing we'd like to minimize with the smooth density we're interested in has a nice score. Here is a simple example, but more generally, if you imagine your P0 has density with respect to Lebesgue, you'll have a nice score, but the empirical score has this very undesirable properties as t goes to 0. And all the action, not all the action, but a lot of the action in this method takes place as you get close to t is 0. And so this is the root cause of why this methodology memorizes and behaves poorly. Any questions about that figure?
I worked on this for a while, 3 years ago.
Okay.
So we were trying to just do a diffusion modeling for a known Gaussian mixture.
Mm-hmm.
And then you train your model for the Grandma field, right?
Yes.
And when I predicted, it's always a constant, irrespective of the data point. So that means that the density it's representing is like a linear, which is not a feasible density. Because we try to...
It's not integrable. Yeah.
Yeah, it's not a valid density. So the density corresponding to what we get.
Mm-hmm.
So I was wondering, because it's a very simple example, we took a few versions, make sure that even an identity matrix, but just the sigma different for the different mixture that's common. So wondering how that, because the number of data points that you have is very small, and the number of network parameters that you try to train are huge. So it's...
I'll come back to that.
Yeah.
That's the right kind of question to be asking about regularization. Then I will come back to exactly that question. All right, so this is a general statement of what you're saying here. So the score looks like this. So Sn is this empirical minimizer. And it looks like this. It's -1 over sigma squared, which is the accumulated variance, x minus uppercase xn. Uppercase xn is a weighted sum of all the data points. And the weights are, the weights sum to 1 and are positive. So you can think of them as probabilities. And the unnormalized weights look like this. And immediately you can observe something, which is that if the x0n are the data points indexed by n, so 0 just means we're at time 0, which is where the data is given, and n is indexing the data point. So the weights, so this score looks like x minus, as a vector field, it's x minus a linear combination of the data. But the combination here is non-linearly dependent. So the span of this is determined by the data in RD, but with non-linear coefficients. These sum to 1 are positive, so probabilities, and this is what the weights look like. So you can see something from this immediately. If x is closer to one data point than all the others, and if sigma squared is tiny, which it will be as t goes down to 0, always, then one of these weights is going to be way bigger than all the others. And so, roughly speaking, the minimization problem is caused by exactly that phenomenon. Once you get close to one data point, you're further away from others. And as the variance gets small, as it must do when t goes down to 0, one of these weights goes to 1 and the others go to 0. So it's exactly the same problem as happens in particle filters. It's a weight collapse problem. And this xn will start to look like a single data point. And then after that, you can deduce memorization. So we'll come back to that. But given this xn, given this xn, we'll come back to it by analyzing it with a time change that makes it a bit more apparent. The reverse SDE just is found by multiplying by -1/2 g the score. So you get this. So this is the reverse problem. And there is a reverse SDE that's similar.
ask a question? So
Yeah.
it feels like you're sort of driving us. So if you were to do regression, for instance,
Yes.
and you have your regression function on data, so you have your observed data, then in a sense you would also, like, if you didn't restrict your class on which you are doing the regression, you would also like interpolate. So
Yes.
you would also
Yeah.
overfit, which is a bit what you're describing
Yeah.
here in a sense.
Yes. Yeah. So if you don't, if you just do density estimation,
Yeah.
if you don't do something to penalize the class over which you're working, you'll get a bad fit. This is exactly this.
And so so here, what this would mean in a sense, if you don't do something a bit more clever, is that if you're using this neural network that are so good at approximating, they would overfit. They would do as if you were learning S capital N instead of trying to do something else.
Yes, and I'll show you that that's exactly what happens. So I'll give you the quick response to what you're saying, which is absolutely spot on. So in this field, there's 1 million people solving this problem, and they're all interested in one version of it, which is where the data comes from images. Those 1 million people communicate with each other, and they have found through a genetic algorithm amongst human beings values of the parameters which solve the problem you've just talked about. Namely, they can get this to work on a specific data set or specific types of data set where they're balancing the regularization that comes from the function class, which in their case is neural networks, with the amount of data that they're typically working on. So if you speak to lots of people in this field, they say it's solved because they can solve the problem they first care about, which is images, although there are problems, even as I've shown you here. I would say it's not solved if I want to view this as a general methodology for sampling, because that field learned nothing about how to regularize and address the question you've just raised if you have a different data set where the data comes from something else. So the take home from my talk is that we should, as mathematicians and statisticians, develop a more principled approach to regularization to address the question that you're raising.
In what sense? Just to follow up on this question, I mean, in some sense, you have n data points and you have an optimization problem where if you then try to learn an n-dimensional Gaussian mixture, you somehow in classical regression, you've just included too many parameters and you should take a subspace or put a penalty or something like that. And so it's just sort of, and then you can ask yourself, well, maybe if I can do a neural network, I can get away without under-parameterizing, so to speak. Isn't that just like a question of the regression as such?
It is under-parameterizing. I mean, the neural network is under-parameterizing. Well, this methodology seems to be competitive in high dimensions. I don't know whether there's a benchmark study that shows that. So I would say, I don't disagree with anything you're saying, but given that this methodology appears to work well in high dimensions, if one wants to use it beyond the setting that it's currently used, one in terms of data, one needs to know how to regularize in a principled way. Currently, it's just neural networks are under-parameterizing if they've been set up correctly, and if they haven't been set up correctly, you'll get memorization. It doesn't work, which you saw in those examples at the beginning. Of course, the thing with the ML community, once any example like that is published, then everyone goes and retunes and they get a better code, and those examples go away. But there'll be other ones because there isn't a theory. So I am, as a mathematician, I don't have to convince you or you. I think there should be more theory in this. All right, so I'm going to change time. So the whole thing is a bit complicated to analyze as it was, because it involves integrating backwards from t, uppercase T, to 0, where there's a singularity. I'm going to change time so that integration backwards becomes integration from S0 to infinity. And I'll do that by writing S is minus a half log sigma squared t. And the S0 is just what you get from the final time when you do this. And then I'm going to rewrite the equation for x, x of t will become an equation for y of s. And what I called uppercase xn, which is a linear combination of the data as a vector field, will become yn. That will be a linear combination of the data as a vector field. So we get this equation. So you see from this that actually G doesn't matter, because in this new coordinate system, G has disappeared completely from the problem. So in fact, G is totally irrelevant to this methodology. You might as well just set it to be 1. Because all different G's map onto this same canonical problem. So this is just, okay, it's just this, where Y is a linear combination of the data. Same thing as before. These weights are probabilities. So they sum to 1, they're positive, and they come from renormalizing the omega tildes, which look like this. And the S is now going to infinity. You see that if Y is closer to any one data point and S is large, the largest weight is going to be the one associated with the data point that Y is closest to. And asymptotically, as S goes to infinity, this weight will, if Y is closer to any one data point than others, then this weights will collapse, become 1 at one point and 0 at all the others. So that is the memorization phenomenon. So just stated succinctly here, if M is the argmin over the indices of, and assume there's a unique such M of a point Y from the data, then approximately when S is large, you just have a linear equation. And that linear equation just drags you exponentially towards the data point. So the main theorem is this. The Voronoi boundaries are important, so let me just say why. So what I've said is that once you get close to a data point, closer to a data point than any others, then asymptotically when S is large, then you're going to just approximately be governed by this simple equation. So I want to make that into a theory. We need the Voronoi boundaries. So these are the boundaries of points that are equidistant from 2 data points. So here this is just on the plane, but in general, for any 2 data points, there'll be a hyperplane of points which are equidistant from them, and then this Voronoi tessellation is made up by intersecting those hyperplanes. So I'm drawing the picture because this can be a bit technical to take in. This is the Voronoi boundaries localized to a compact set. Turns out we can localize to a compact set because the equation I've written down always, if you start far out, will always point in towards a compact set. So there is a compact set which depends on the data which you enter after a finite time independently of initial condition. So this is simply the Voronoi boundaries compactified. And so that's one piece of notation. You don't need to take it in, just think of this picture, this Voronoi tessellation for the data, and think of the boundaries, but inside everything inside a sphere, which is larger than it's large enough to include all the data. And then just define limit points. This will be the same as an omega limit point for a deterministic dynamical system, for an autonomous dynamical system. This dynamical system is non-autonomous, so I just write the definition anyway. So Y star is a limit point for the equation that I wrote in Y. If there's a sequence of increasing times with the property that if you evaluate Y at those times, you converge to the limit point. And then the theorem is this. There's some details here that you don't need to take in that define this compact set that you enter that is defined by the data. But there is a ball of radius r that everything enters after some finite time, S star. And then there are only 2 kinds of limit points. If Y star is a limit point, then either it's on the Voronoi boundaries compactified, or it's one of the data points. And in the second case, if it's one of the data points, then you have this universal rate of convergence up to a constant. It goes like e to the minus s. So there's a very similar theorem for the OU process, just a bit more complicated because the mean is present. But it has this universality property in terms of rate. And again, really the choice of G as here does not matter. Really didn't matter what G was because G disappeared when I did a time change. Okay, so this says either you end up on the Voronoi boundary or end up at a data point. Well, I did it because you have this singularity, which makes the analysis a bit complicated because things blow up. There are other methods, the methods of Van den Eyden, which are stochastic interpolants and things of that type, normalizing, not normalizing flows, but these things that work on finite time. By the way, they also have exactly the same analysis, and they also have the singularity. You also can transform it away. It's a generic technique for analysis, but I would actually say the numerics should be done, in my opinion, in the transform variable. So here I'm using the ODE, but you can do this time change for the SDE, and there will be a Fokker-Planck equation. It's really just to do with how the G of t will become some function of S. But I would say that the integration for these problems would be better done in S than in T. So there are this is a practical thing. So there are lots of, in the original T variable, there's lots of different proposals out there about how to choose T as how to choose the time step as you go down to T as 0. If you rescale the problem like this, you can see exactly how you should integrate it just by using standard numerical analysis. So that's why I would argue this is a better time coordinate to work in. Richard, I thought you were about to ask a question, but maybe I was wrong. You want to see the picture or the definition?
The first thing is that Y star would be the boundary of one of these sets.
No, the claim is everything enters a compact set, which means I can talk about the Voronoi cell. Then if you are a limit point, then either it's on a Voronoi boundary or it's a data point.
The Voronoi boundary was in the previous picture.
Yeah, so the Voronoi boundary are these. So this is constructed by, for each pair of data points, there's a hyperplane which is equidistant from them. So you take all of those hyperplanes, intersect them, prune out the stuff at infinity, and you get the Voronoi tessellation restricted to a compact set.
Some sort of variational argument.
The proof is a dynamical systems proof that says that if you are not on the Voronoi boundary at some time that's large enough, then you can estimate the flow using this approximation. And then this approximation pulls you further and further away from the Voronoi boundary, so you can prove things uniformly in time. And then this approximation converges to a data point. So either you're stuck on a Voronoi boundary and you can't use the argument I just gave, or you leave the Voronoi boundary, then for large enough time, you will converge.
And the dynamical system then stops in C.
Because it basically just behaves like this linear problem.
So can you actually positive probability, so to speak, that you stay at the boundary?
Not with positive probability. We're trying to prove that. I'm sure that the answer is it only happens with probability 0 with respect to the initial condition that you end up on a Voronoi boundary. Doesn't actually happen it happens with probability 0. Yeah. If with respect to initial condition, yes, that's what I believe. There's a very soft PDE proof for that, but I'll share it with you later, because there's a picture based on the Liouville equation, but it's a bit subtle. So I prefer the dynamical systems proof, which is basically a method of characteristics. Okay, so you do get, you do cross Voronoi boundaries. You see that with this red trajectory here, but eventually you get trapped in a cell. Here's one that never crossed the Voronoi boundary. But in answer to what Richard was just asking about, this is an example. All of these, this is an example with 2 data points. The Voronoi boundary is this line here. And these are trajectories of the dynamical system. If you are on this line here, initially you stay on it. This is provable for this example. And then you will converge to, unfortunately, there are no arrows on here, but you will converge to this midpoint. But any trajectory off here, if you initialize off this line, you converge to one of these 2 data points. So it's what the same picture you would have for a gradient flow if you have a compactifying potential and you have a finite set of equilibria that are disjoint, you will get almost sure convergence to an equilibrium point. And the failure modes for that statement will be things that are on the, so you get almost sure convergence to a local minimizer. The failure points will converge to saddle points, but they will have probability 0, and you have to be on the stable manifold of the saddle point. This is more complicated because it's non-autonomous, and that's why we have not yet proved it, but we are halfway there. I mean, they are, it's because it's non-autonomous, it's a bit more complicated than the gradient picture that I just gave to Richard is kind of the fixed points of the dynamical system in autonomous. Here it is more complicated because the weights, the way the weights behave is very non-autonomous, but it makes it approximately autonomous at the end. Okay, so I just want to talk about regularization. So I'm not going to have time to say all of it in the last 3 minutes. So I just want to kind of summarize it to you very quickly. What happens in practice, as discussed with Judith earlier, is in practice, the field is doing two things. It's under-parameterizing and it's early stopping training. And that has been made to work from a practical point of view on some problems. I want to take a look at being more systematic. So I'm going to look at this version of Tikhonov regularization, where we add a penalty of this type. And there's a paper by Andrei Wibisono, and he looks at, he proves an asymptotic consistency theorem with this regularization of the Gaussian mixture, where rather than dividing by Pn, you divide by the maximum of Pn and some floor. He shows how to choose C as a function of n to get asymptotic consistency, which is nice theoretically, but for the reasons that we discussed earlier is not practical because this involves running through the entire data set to evaluate this at every point in time, which is for large data impractical. Right. So I just want to show you a couple of examples. So this is Tikhonov regularization. This is the Tikhonov regularization parameter. And I'm showing you the fraction of samples that are generated which are memorization or very close to memorization as a function of regularization parameter. If regularization is 0, we know that all of the data points are memorized if we believe that you don't get stuck on the Voronoi boundary. And that's indeed what you find. So with no regularization, all the data is memorized. But as you bring up the regularization, you decrease the fraction that are close to the data set. The same thing with Andrei Wibisono's regularization. His floor parameter affects the proportion that are memorized. Right, so now this is what's done in practice. You can also, so now I'm turning to neural networks. So these two, this Tikhonov and Wibisono, were based on using the Gaussian mixture. Now looking at what is done when you use a neural network, and I'm looking at the effect of early stopping. So I'm looking at the number of epochs in a fairly over-parameterized setting and the fraction of memorized. So you see that if you train for long, you end up memorizing everything. You can also look at the effect of under-parameterization or over-parameterization. So here we have a large number of parameters. We again memorize entirely.
Can I ask you, so when you say over-parameterization or under-parameterization, how do you play the game? Are you like considering sort of fully connected neural network and then you put some of the weights to 0?
No, I'm just playing with the network width. So fully connected and just looking at a sequence of problems
so
with a greater and greater network width. And so this is the network width. And then if it's small, a small fraction are memorized. But once you get up here, you see a phase transition that's more or less memorizing everything.
Yeah. So the sample that don't match the data, how do we know that it really came from?
Yes, we do for Andrei Wibisono because he has a theorem. about how to choose C as a function of n to ensure that that answer to your question is answered. But the conclusion of my talk is we don't know that, and we should know that. If we want this to be a statistically well-founded method that isn't just tuned to work on images, then we need theory about how to regularize to ensure that.
So there are some theoretical results that sort of say something along these lines, like there was a paper by Suzuki first that was saying that if you have data with a density on 0,1 to the 0,1 to the power capital D, say,
Yes.
then it's got if the sparsity of your network, or the number of nodes, so the complexity of your network, which is like under parameterization in your context,
Yes.
is controlled by terms that depend on sort of the usual statistical kind of control in terms of entropy, in a sense. Then you get the min-max rate of estimation, and then we had the sort of extension of that with assuming that your data live on a manifold, and you also have these results.
Were they using diffusions or you? Or,
using
okay.
diffusions.
I'm not familiar with those results, so I would like to know about them.
Yeah, I can send you the
Thank you.
papers. Yeah. So, but it's always done because it follows a sort of a theoretical result by Johannes Schmidt-Huber in a sense, but it's always done using the idea that if the size of your network is controlled by this number
By
of
sparsity.
non-zero coefficients, in a sense, this is what you get. And maybe with a regularization, you can arrive at this level and then get the result. Right?
Yes.
It's probably what you would sort of expect, I imagine.
What you would like.
That would what you would like,
Yeah.
yeah.
Thank you. I would really need to know about
Yeah,
those, so
yeah.
thank you. I won't need to finish. So this just shows you that there's a singularity in the score from the Gaussian mixture. This shows that when you learn it, here I'm combining Tikhonov regularization with neural network and showing that the Tikhonov regularization affects how the singularity is controlled. I have some examples here which are interesting with respect to images, but I think I will stop because I've taken more than the hour. And I've also answered lots of questions as we go along, so I can just stop now. Thank you for all the questions. That was great. I'm happy to take them, but I'm aware that I've gone on probably for a whole hour, so we had questions as we went. I don't want to take these people's time, so I'm happy to answer them afterwards.
So in the graph that you show like the fraction of memorization data.
Yeah.
For the experiment, how did you do this?
Thank you. That's a good question, because actually we have to set a threshold in there, which I've not told you. So, because it's not exact memorization, it's getting within epsilon neighborhood of the data. So there is an epsilon in there which we chose to define having memorized. And that was just chosen empirically so that for the data that we looked at it, which will either be in this weird, I didn't have a time to show them these images. It was just chosen to be sensible with respect to this example. And in the other ones that were just in 2D, it was just a small epsilon neighborhood where small was relative to the separation, minimal separation between data points. Thanks. A very good question. Yeah.
Slightly woolly question, I guess. But so when you regularize or you've trained to a number of viewpoints, how does that affect like, the quality of the images you generate? If you're not memorizing very well, does it just make things that don't look like the thing you started with?
Yeah. So of course, again, this comes back to how the field has worked. There's a brilliant article by Donahoe, which I would recommend reading. I don't know if you've read it, called Data Science at the Singularity or some title like that. But he makes a very good case for the idea that this field has been successful because they share the same data sets, they share the same algorithms, and they share information about how those algorithms are performing. And so there are a very large number of people working on a single problem. And so, of course, you see images all the time. You can go and find them online. They're impressive. The old ones like DALL-E tend to look like cartoons and very unattractive. But if you go to ChatGPT 4.0, the Pro version now and get the best image generator in there. It's incredibly high quality, photorealistic. So I could put a photo of you in there if you gave me one and say I wanted a photo of you at a dinner party with Bill Clinton, and it would look realistic. But that's happened not because of any knowledge of, other than large number of people working and tuning until that happens, not based on theory. So things do work well on these problems that are where there are a lot of people learning how to make them work. On my examples, just to complete the question, you can see it a little bit with these. So this is a baby example. There are just 2 data points, but these are functions, right? They're blue and yellow. These are the kind of things you get from early stopping. So they have, interestingly, geometry is preserved, but they're not exact rectangles. You go a bit further in the training, they start to look more exactly like these rectangles, but you do get, things that are not in the data set. You run it long enough, you just repeat the data set. But if the other examples that we did were based on this, and so here there's no interpretation of these points, they're just points in R2. The effect of regularization is to blur these out and get pieces of data near to them. Thanks.
Hi. I would like to come back to the choice of regularization, so in terms of regularization, and the link with the dynamical equation, the equation of the dynamics. I would like to ask you if, in a context of reproducing kernel reverse space, there should
of RKHS?
Yeah, cache. Should be a way to, because your score, of course, is part of the equation, so your choice of regularization is meaningful compared to that. And I wanted to ask you if you have worked on this direction.
Thank you.
Choosing the kernel, thinking about
that question. So thank you for bringing that up. The answer is there are 2 points there. So the regularization is in both space and time, and you're talking more about the regularization in space by the choice of an RKHS. We have, in the conditional case, we have some thinking in that direction, but that's incomplete work. With respect to time, this Tikhonov regularization, the way I've set it up, has an effect which is, roughly speaking, that you no longer integrate to infinity. So the problems I described were to do with integrating to infinity, which is when you get the weight collapse that I described. So this regularization provably is basically saying you no longer integrate to infinity, and then you can mathematically understand how the memorization is ameliorated. Doing this with RKHS would be interesting. There is a paper, really, just to come back to Andre Wibisono, the problem with this is, as you pointed out right at the beginning of the talk, it involves running through the whole data set, which you don't want to do. There's a paper of Justin Solomon, who is at MIT, and his group, where they have looked at something that has a flavor of RKHS, where they're summarizing groups of data together, which you might imagine is the kind of thing you would get out of using an appropriate RKHS to summarize the data. But it's a very empirical, hand-waving paper, but quite interesting. Thank you.
Can I ask another question, or you
want
to stop? And you want
No, I don't want to stop, but I'm worried that other people might want to leave the room. So I'm happy to stop and carry on answering questions, but it's up to our chair.
One last question.
All right, thanks. So going back to this, so typically, like in traditional statistical problems, you would pick up a regularization having in mind some kind of smoothness of your object or something like that.
Yeah.
Which doesn't seem to appear here in your Tikhonov regularization, because you only have a constant, so it doesn't. So usually that would be like more associated to the number of derivatives or something like that. And
I mean, that's why I say Tikhonov and not Tikhonov-Phillips, by the way, because Tikhonov's original regularization was L2. Yeah. I mean, this is L2 weighted by the density, and Phillips was added Sobolev spaces. Indeed, the smoothness class might be relevant. On that point, and you mentioned this earlier, there's a lot of belief for images in this manifold hypothesis for the data. So there is work that looks at regularization from the point of view that the data is not Lebesgue density, doesn't have Lebesgue density. And okay, so
but we didn't use regularization. We used this sort of under parameterization in a sense. So that was a different kind of result.
it is a regularization.
Yeah,
but,
and it's not what people do in practice. So this is a bit like so we say if the network has this sort of sparsity in it, in a sense, or this sort of complexity in it, then this is a rate that you get, and so you get the rate that you want to have. But it would be interesting to see whether you can sort of achieve this result by forcing
to
regularization
to have that sparsity.
To obtain at the end of the day sort of this sparsity.
Yeah. Yes, I don't know the answer to that, but there's hope for that based on other simpler problems in statistics.
Yeah.
L0.
In the interest of time, let's thank the speaker again.
Thank you.